So, good evening, everybody. So, today I welcome to our resource expert, Dr. Chandrashekar Shetty, sir, and I also welcome to our Academy President, Professor Ayapan, sir, and I welcome to our CEO, Chief Executive Officer, Dr. Ramesh, sir, and all attendees. So, I will give to small introduction about Dr. Chandrashekar Shetty, sir, having some education qualification, MSc Physics, Master of Philosophy in Physics, postgraduate diploma in computer applications, having bachelor education B.Ed and MSc Information Technology, and having KSET, and sir having PhD Physics from Mangalore University from Nonlinear Optical Materials. So current position having head of the Department of PG Studies and Research in Physics, Research Coordinator for DST, FAST program, and also mentor DST Inspire program, Government of India. Sir having teaching experiences and academic responsibilities. Teaching in the of the department MSc Physics at St. Elias College, Mangalore from July 2012. Joined as a lecturer in the Department of Physics and Electronics at the St. Elias College, Mangalore. So 10th July 1998. And having summer research fellowship selected for summer research fellowship by Indian Science Academy of Sciences and worked on the topic of EPO studies on Mangalore at the Department of Physics, Indian Institute of Science, Bengaluru during July 2018. And selected for summer research fellowship by Indian Science Academy of Sciences and worked on the topic determination of the elastic constants of a pneumatic liquid crystal using pre-dielectric effect at Raman Research Institute, Bengaluru during May-June 2013. And also, Sir published 20 research papers, which include the following journals: Material Letters, Optical Materials, Journal of Applied Physics D, Optic International Journal for Light and Electron Optics, Journal of Molecular Structure, Results in Physics, Journal of Optics and Laser Technology, Materials Today Proceedings, Journal of Materials Technology, Journal of Materials Research Innovations. And Sir presented research papers in 14 international conferences, extracurricular activities, worked as Associative NCC Officer in Army Wing of NCC in the rank of Lieutenant from July 2005 to July 2009. Thank you, sir. Over to you.
Thank you for the nice introduction. Once again, I thank all KST office bearers and representatives for giving this opportunity. I'll try to speak in Kannada as well as in English so that it will benefit larger crowd in the state of Karnataka. ಇವತ್ತು ನಾನು ಮಾತಾಡಬೇಕಂತ ವಿಷಯ ಅಂದರೆ ವಿದ್ಯುತ್ ಕಾಂತೀಯ ಅಲೆಗಳು, that is electromagnetic waves. Today we're all very lucky to have several aspects of communication. ಅದು ರೇಡಿಯೋ ಇರ್ತದೆ, ಅಥವಾ ಟಿ ವಿ ಇರ್ಬೋದು, ಮೊಬೈಲ್ ಕಮ್ಯುನಿಕೇಷನ್ ಇರ್ಬೋದು, ಸ್ಯಾಟಲೈಟ್ ಕಮ್ಯುನಿಕೇಷನ್ ಇರ್ಬೋದು. ಎಲ್ಲ ಕಮ್ಯುನಿಕೇಷನ್ಸ್ ಅಂದರೆ ದೂರಸಂಪರ್ಕ, ಇದರ ಮೂಲಭೂತ ಅಂಶವೇ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್. ಈ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್ ಅಥವಾ ವಿದ್ಯುತ್ಕಾಂತಿ ಅಲೆಗಳು ಬಹಳ ಒಂದು ಅತ್ಯುತ್ತಮ ವಿಮರ್ಶೆಗೆ ಒಳಪಟ್ಟಂತಹ ಒಂದು ವಿಷಯ. ಇದು 1870ರ ನಂತರ 1914ರ ತನಕ ವಿಶೇಷವಾಗಿ ಎಲ್ಲರನ್ನು ಆಕರ್ಷಿಸಲ್ಪಟ್ಟಿತ್ತು. ಆನಂತರ ಅದರ ಎಲ್ಲ ಗುಣಧರ್ಮಗಳು ಜನರಿಗೆ ಅರಿವಾಯಿತು. ಆನಂತರ ಇದು ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್ ಅಂದರೆ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಎಂಬ ಒಂದು ಸಬ್ಜೆಕ್ಟ್ನ ಮೇಲೆ, ಒಂದು ಟಾಪಿಕ್ ಮೇಲೆ ಇದರ ಅಧ್ಯಯನ ಆರಂಭ ಆಯಿತು. ಆರಂಭಕ್ಕೆ ನಾವು ಅದರ ಸ್ವಲ್ಪ ಇತಿಹಾಸವನ್ನು ನೋಡಿದರೆ, ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್ ಪ್ರೊಡ್ಯೂಸಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಎಲ್ಲರಿಗೆ ಗೊತ್ತಿರುವಂತಹ ವಿಚಾರ, ನಮ್ಗೆಲ್ಲರಿಗೂ ಗೊತ್ತಿದೆ. ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್ ಪ್ರೊಡ್ಯೂಸಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್. ಈಗ ಅದೇ ರೀತಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಪ್ರೊಡ್ಯೂಸಸ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್, ಇದು ಕೂಡ ನಮ್ಗೆ ಗೊತ್ತಿದೆ. ಈ ಎರಡು ಆಧಾರದ ಮೇಲೆ ನಾವು ಮುಂದೆ ಹೋದ್ರೆ, ಈ ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್ ಸ್ಟಡಿ ಕರೆಂಟ್ in a wire produces magnetic field around it. ಇದು ನಮಗೆ ಬಹಳ ಸ್ಪಷ್ಟವಾಗಿ ಗೊತ್ತಿದೆ. ಎಲ್ಲ ಸಣ್ಣ ಕ್ಲಾಸಿಂದ ನಾವು ಅದನ್ನು ಓದ್ತಾ ಬಂದಿದ್ದೇವೆ. ಆದರೆ ಈ ಸ್ಟಡಿ ಕರೆಂಟ್ ಮೂವಿಂಗ್ ಕರೆಂಟ್ ಆದರೆ ಅಥವಾ ಆಲ್ಟರ್ನೇಟ್ ಕರೆಂಟ್ ಆದರೆ ಆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನಾಗ್ತದೆ ಎಂಬುದು ಒಂದು ಜಿಜ್ಞಾಸೆಯ ವಿಷಯ. ಹಾಗೆ ಮುಂದಕ್ಕೆ ಹೋದ್ರೆ, ಈ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್ ಅನ್ನು ನಮಗೆ ಬಹಳ ಸ್ಪಷ್ಟವಾಗಿ ಕೇವಲ 4 ಇಕ್ವೇಶನ್ಸ್ ಮೂಲಕ ನಮಗೆ ತಿಳಿ ಹೇಳಿದವರು ಜೇಮ್ಸ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್. ಅವರು ಕ್ಲಾಸಿಕಲ್ ಥಿಯರಿ ಆಫ್ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ರೇಡಿಯೇಷನ್, ಇಟ್ ವಾಸ್ ಫಸ್ಟ್ ಥಿಯರಿ ಟು ಡಿಸ್ಕ್ರೈಬ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ, ಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಅಂಡ್ ಲೈಟ್ as different manifestations of the same phenomenon. ಯಾವಾಗ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ, ಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಮತ್ತೆ ಲೈಟ್ ಇದು ಮೂರೂ ಕೂಡ ಒಂದೇ ವಿಷಯದಿಂದ ಮಾಡಲ್ಪಟ್ಟಿದೆ ಎಂದು ನಮಗೆ ತಿಳಿ ಹೇಳಿದವರು ಜೇಮ್ಸ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್. ಅವರು ತಮ್ಮ 4 ಇಕ್ವೇಶನ್ ಮೂಲಕ ಅದನ್ನು ನಮಗೆ ತಿಳಿ ಹೇಳಿರ್ತಾರೆ. 4 ಫೇಮಸ್ ಇಕ್ವೇಶನ್ಸ್ ಆಫ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್ ನಾವು ಅವತ್ತು ನೋಡ್ತಿದ್ದೇವೆ. ಇದಾಗಿ ಸುಮಾರು 20 ವರ್ಷಗಳ ನಂತರ ಹೆನ್ರಿಚ್ ರುಡಾಲ್ಫ್ ಹೆರ್ಟ್ಜ್ ಎಂಬುವರು ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್, ವಿದ್ಯುತ್ಕಾಂತಿ ಅಲೆಗಳನ್ನು ಡೆಮಾನ್ಸ್ಟ್ರೇಟ್ ಮಾಡಿ ತೋರಿಸ್ತಾರೆ. ಪ್ರಯೋಗಾಲಯದಲ್ಲಿ ಅದನ್ನು ಉತ್ಪಾದನೆ ಮಾಡಿ ಮತ್ತೊಂದು ಕಡೆ ಅದನ್ನು ಡಿಟೆಕ್ಟ್ ಮಾಡ್ತಾರೆ. ಈ ಸೆನ್ಸ್, ಪ್ರೊಡ್ಯೂಸ್, ಸೆನ್ಸ್ ಅಂಡ್ ರಿಸೀವ್ಡ್ ದ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್. ಇವತ್ತಿನ ಎಲ್ಲಾ ಬೆಳವಣಿಗೆಗೆ ಬಹಳ ಮುಖ್ಯವಾಗಿ ನಮಗೆ ಬೇಕಾದ್ದು ಈ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ವೇವ್ಸ್. ನೋಡಿ, ಇದು ದ ಫೇಮಸ್ 4 ಇಕ್ವೇಶನ್ಸ್ ಆಫ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್. ಇದು ನಾವು ನೋಡಿದ್ರೆ
Hello, sir. Hello. Hello.
Sorry, it muted, I suppose. Now, can you
Yes,
hear
sir.
me?
Yes, now audible, sir.
Yes, all right. Okay, sorry. Line integral, first equation I explain again. Line integral over a closed surface E dot dA. Electric field is E. dA is the area of that loop. Is equal to Q by epsilon naught. Q on the charge associated with that loop. That is Gauss law for electricity. Similarly, the second equation, line integral over closed surface B dot dA, B is the magnetic field, dA is the area of that loop, is equal to 0. That is Gauss law for magnetism. ಮೂರನೇದು line integral over E dl over a closed surface, that is equal to minus d phi by dt. Phi is the magnetic flux density. That is called Faraday's laws. ಅದೇ ರೀತಿ ನಾಲ್ಕನೇ equation, line integral over closed surface B dot dl is equal to mu naught plus IC plus mu naught epsilon naught d phi by dt. d phi electric flux, mu naught permeability of free space, epsilon naught permittivity of free space, IC is the conduction current. That is Ampere's Maxwell law. ನಾವು ಈ ಆಂಪಿಯರ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್ ಲಾಕ್ಕೆ ಹೋಗುವ ಮೊದಲು ಈ ಮೂರು ಇಕ್ವೇಶನ್ಸ್ ಅಲ್ಲಿ ಯಾವುದೇ ಸಮಸ್ಯೆಗಳು ಬರಲಿಲ್ಲ. ಆದರೆ ನಮಗೆ ನಾಲ್ಕನೇ ಇಕ್ವೇಶನ್ಸ್ ಬರುವಾಗ ಇದು ನಾವು ಆಂಪಿಯರ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್ ಲಾ ಅಂತ ಹೇಳ್ತೇವೆ. ಇದನ್ನು ಫಸ್ಟಿಗೆ ಮ್ಯಾಕ್ಸ್ವೆಲ್ ಕೊಟ್ಟಿದ್ದು, ಇದು ಕಂಪ್ಲೀಟ್ ಆಗಿರಲಿಲ್ಲ, ಇದು ಅರ್ಧ ಮಾತ್ರ ಕೊಟ್ಟಿದ್ರು. ಅದಕ್ಕೋಸ್ಕರ ಆ ಪ್ರಾಬ್ಲಮ್ ಏನು ಇನ್ಕನ್ಸಿಸ್ಟೆನ್ಸಿ ವಾಟ್ ವಿ ಒಬ್ಸರ್ವ್ ಇನ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್ ಲಾ ಹ್ಯಾಸ್ ಟು ಬಿ ಸ್ಟಡಿಡ್. ಅದನ್ನು ನಾವು ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್ ಎಂಬುದರ ಮೂಲಕ ಕಲಿತೇವೆ. This is what I explained here. Electromagnetic waves which are coupled time varying electric and magnetic fields that propagate in space. Light is an electromagnetic wave. Maxwell's work unified the domains of electricity, magnetism and light. I already explained you these things. Now here when I say electric current as well as magnetic field, both are interconnected. How do you understand that? Moving electric current generates magnetic field. Similarly, moving any magnetic field generates electric current. It has to be understood by a common man. Therefore, the fourth equation, while applying the Ampere circular law to find magnetic field at a outside the capacitor connected to a time varying current, that I'll explain to you, Maxwell noticed an inconsistency in the Ampere circular law. He suggested the existence of an additional current called by him as displacement current. ಅದು ಕಾರಣ ಸ್ಟಡಿ ಕರೆಂಟ್ಗೆ ಯಾವುದೇ ಸಮಸ್ಯೆ ಬರಲಿಲ್ಲ. ಯಾವಾಗ ಕರೆಂಟ್ ಚೇಂಜ್ ಆಗ್ತದೆ, ಆಲ್ಟರ್ನೇಟ್ ಕರೆಂಟ್, then he noticed the problem in the Maxwell's equation. Then he rectified that problem by the addition of one more term called displacement current. We'll try to understand that displacement current in a more detailed way. Okay. Now what is displacement current? For that, you consider a capacitor C. I have shown here capacitor C, which is charged. Okay. Now you know that any charged capacitor here, this is charged through a current, is passing through it, and current is a time varying current. That means with respect to time, the current changes its magnitude. Therefore, time varying current, magnitude as well as direction also can be changed if it is an AC. Then at a point P, which is outside the capacitor, we want to know what is the magnetic field. Okay. Therefore, by charging a capacitor, we can expect a magnetic field outside the capacitor. So what is the quantity of the magnetic field? So you can always you can think of a circular loop here of radius r, a circular loop of radius r, whose plane is perpendicular to the direction of the current carrying wire. Therefore, a plane which is perpendicular to current carrying wire, and it is symmetric either side, symmetric with respect to the current carrying wire. Therefore, what is the magnetic field? Now you know that magnetic field is always directed along the circumference of the circular loop. Magnetic field is always directed along the circumference, because you know current is flowing like this. You can apply right hand thumb rule and you see that you can see the current direction which is perpendicular to the outer circular loop of the wire. Okay. Therefore, if you see the calculate the magnetic field, we apply again a line integral over the closed surface, that is B dot dl. D is the total line segment of this area, that is equal to mu naught into I. Again, I am taking as a time varying current. Okay. Now, from this, I know what is the area of that line segment. Line segment has got area of 2 pi r, that is the circumference of that circular area. Therefore, B is equal to B into 2 pi r. I integrated over the entire circular loop. Therefore, B into 2 pi r is equal to mu naught into I. There is no problem getting this equation. Now, we consider a different surface. Let us say I have taken a different surface here, the same capacitor, same loop is there, point P is also there on the surface of that loop. I am taking a bigger surface here, you can see, which is blue colored mark. This is a pot-like structure which nowhere touches the current carrying conductor. You can see this surface do not touch the current. And but it has its bottom between the capacitor plates. Bottom, you can see it is in the inside the capacitor, part of it is inside the capacitor plates. Its mouth is on this outside part, that is mouth is the circular loop of the original loop. You could see this. Now, again, if we apply the Ampere circular law as we applied in the case of first, what is very strange is, according to the Ampere circular law, wire is not carrying circular loop is not carrying any current. Therefore, what do you expect? We expect the right hand side of this equation B, right hand side of the previous equation B, that is must be equal to 0, because B into 2 pi r is equal to 0. Left hand side remains the same, but right hand side is same. Therefore, what is missing in this case? For that, we have to look at to in a very serious manner the missing term to be identified. That is, we have not taken care of the electric field which is present between the plates of the capacitor. Therefore, what is the electric field? Suppose you take A is the area of the capacitor plates, Q is the charge associated with it, then electric field is given by 1 by epsilon naught times Q by A. And this field is perpendicular to the plates, that is directed from positive charged plate to negative charged plate. And it has the same magnitude over the entire area. It has the same magnitude. Okay. Therefore, if I look at the capacitor plates, field is not there outside, but it is present inside. So I have to look at the electric flux. What is the electric flux? When I look at the electric flux, that is electric field into the area of the plates. If I substitute here, then it becomes 1 by epsilon naught Q by A into A, that is Q by epsilon naught. Therefore, now I could see the electric flux is present, and if I think of time varying current, then I must think of rate of change of flux. So what is rate of change of flux? In the third diagram, we are showing the rate of change of flux here. That is, you can see again the electric fields are shown from left to right arrow marks. The similar diagram is just the shape of the outer curve change. That is the area, the blue colored area is taken inside here. You could see all other things are same. Then, if I think of rate of change of flux d phi by dt, then that will be d by dt of q by epsilon naught. Then I can write it as 1 by 1 by 1 by epsilon naught d phi by dt, or you can rearrange to left hand side, then epsilon naught times d phi by dt is equal to I. Now you could see the current is rate of change of flux, electric flux. Now this is the missing term in Ampere's electrical law. Therefore, the Maxwell's fourth law had a difficulty with this term. This was not present. Therefore, if we generalize this law by adding the total current carried by the conductors through the surface, another term which is epsilon times the rate of change of electric flux through the same surface, the total has the same value of current I for all surfaces. This is very important thing. We see that total current remains the same. Now, if you look at the magnetic field B at a point P outside the plates is same everywhere at a point M just inside as it should be. The current carried by the conductor due to the flow of charges is called the conduction current and is due to changing electric field or electric displacement. It is therefore called displacement current or Maxwell's displacement current. Therefore, Maxwell equation, the fourth equation is improved by Ampere by adding a term called displacement current. Okay, that's very important point to be understood. Therefore, the source of magnetic field, the conduction, electric current due to flowing charges, but also the time rate of change of electric flux. Therefore, source of magnetic field is not only due to the steady current, but changing current also contributes for the magnetic field. More precisely, if you look at that, the total current I is the sum of the conduction current denoted by IC and the displacement current denoted by IT. Therefore, effectively, if you think of a capacitor in which current is flowing, you have two components. One is conduction current and ID. It not only capacitor inside I am talking about, the surrounding region of the capacitor where we want to measure the magnetic field. Therefore, outside the capacitor plates, we have only conduction current IC and no displacement current. ID is 0. Conduction current is present outside. Inside, outside displacement current is not present. ID is 0. Similarly, inside the capacitor, there is no conduction current. Inside the capacitor, there is no conduction current. IC is 0. There is only the displacement current IC. Effectively, we have both, that is IC plus ID. Okay, either side. One is some part is present inside, some part is present outside. Now, therefore, say now you can visualize the direction of the magnetic field inside the capacitor plates. I consider the same capacitor. Current is flowing, changing current. You can see the direction of electric field. This arrows from left to right inside the capacitor. Capacitor is charged. You can see plus and minus signs. You can think of the magnetic field M at a point M shown by this thick arrow mark B, and these dotted lines represent the magnetic field. Dotted lines represent the magnetic field. And same thing as can be viewed as a cross-sectional view. If you look at it, see the electric field is represented by this arrow mark R, that is the outer radius and inner radius. At every point, you see that magnetic field direction changes. Magnetic field direction changes. Whereas this X is the direction of the electric field. Therefore, electric and magnetic fields E and B between the capacitor plates at a point M and a cross-sectional view of the figure. You can see here electric and magnetic field and the cross-sectional view of the same thing can be viewed like this. Therefore, line integral over a closed surface V dot dl is equal to mu naught plus IC plus mu naught epsilon naught d phi by dt. This is the famous equation, that is fourth equation, now known as Maxwell law, Ampere's and Maxwell law together. Therefore, after understanding the significance of this displacement current, which is present when the changing electric current is passing through the capacitor, it completes the Maxwell's the fourth equation. Now, this leads to the idea of electromagnetic wave. Therefore, today we know that stationary charges produces electric field. It is known to us. Whereas charges in uniform motion, steady current produces magnetic field. Therefore, whenever there is a accumulated charges, we have studied electrostatics, you find that electric charges are available. When charges are in motion, steady current, changing positions of electric charges, that is moving charges, that lead to the steady currents. Around the current carrying conductor, you know that there is a magnetic field. Now you see, the question comes is, accelerated charges radiate electromagnetic waves. Therefore, charges has to be accelerated. It has to move with different velocities, accelerated rate. Then it will produce electromagnetic wave. Therefore, what you have to think? We have to think of a charge oscillating with some frequency. Consider a charge oscillating with some frequency. This produces an oscillating electric field in space, which produces an oscillating magnetic field also. Therefore, it is a source of oscillating electric field and magnetic field. Whenever a charge is moving with acceleration, there will be electric field as well as a magnetic field. Both are oscillating electric and magnetic fields. Therefore, the oscillating electric and magnetic fields generate each other. They are coupled together. Hence, when they move in space, we say the wave is propagated in the space. Therefore, a coupled electric and magnetic fields oscillating each other and move in space result into electromagnetic wave. Therefore, now you can visualize an electromagnetic wave as a combination of electric field and magnetic field, which are produced due to accelerated electric charges. You can do it otherwise also. Accelerated magnetic field also can produce electric field. Therefore, in the year 1987, Henry Hertz, he successfully produced the electromagnetic wave. That is known as Hertz experiment. He produced electromagnetic wave as well as he detected electromagnetic wave. Therefore, production and detection of electromagnetic wave is done for the first time by Henry Hertz. That is known as Hertz experiment. Later, after 1 or 2 years, Indian scientist Jagdish Chandra Bose observed the electromagnetic waves of wavelength of 5 millimeter to 25 millimeter. He is successfully able to produce the electromagnetic wave. That was a historic event by Jagdish Chandra Bose. Of course, he did not take it further because he was involved in teaching in a university. But the same experimental evidences are continued by Marconi, that is the Marconi was successful in transmitting electromagnetic waves over distances of many kilometers. That is that will lead to the first communication and he was awarded with the discovery of radio. Therefore, Marconi successfully used electromagnetic waves for the communication to few kilometers, so that he could get the credit of generating or producing the first radio with the help of two-dimensional plane like this. You could see, say X, Y, and Z. Three are the X, Y, and Z, three directions. And along X-axis, I represent in the first picture, it is electric field. Along Y-axis, you could see the magnetic field here. This is electric field, and along the Y-axis, you see that is magnetic field. Then Z is the direction of propagation. And you see, when in the one loop electric field is shown in the upper direction, in the second loop it is shown in negative direction. Next again upper direction, positive and negative direction. That means it represents an oscillating electric and magnetic field. And say this is a view of a linearly polarized electromagnetic wave propagating in the Z direction, with the oscillating electric field along the X direction and oscillating magnetic field along the Y direction. Therefore, an electromagnetic wave can be represented in this way. Now, the X component of this electromagnetic wave can be written as Ex. Ex is E naught sine kz minus omega t. Here, Ex is the X component of electric field. E naught is the amplitude of that. K is 2 pi by lambda, that is called wave vector. 2 pi by lambda, lambda is the wavelength. K is 2 pi by lambda, and Z is represents the direction. Omega is the angular frequency. T is the time rate at which it moves. Similarly, the magnetic field component, which is in the Y direction, is represented as By is equal to B naught. Again, B naught represents the magnitude. Sine kz minus omega t. Kz minus omega t. Okay. Therefore, electric and magnetic field components can be represented in this manner. Now here, once I know the electric and magnetic field, there are several aspects which are associated with that. One or two just things I'll discuss first. So we know that omega can be represented by C by K, where C is the speed of light. C is the speed of electromagnetic wave. Similarly, now if I take C, which can be observed as 1 by square root of mu naught and epsilon naught. Mu naught and epsilon naught values are known for free space, and if I substitute this mu naught and epsilon naught value, it will lead to the velocity of electromagnetic wave. That's nothing but the speed of light. Similarly, frequency, if I take nu and lambda wavelength, that also will give you C, that is the speed of light. Nu into lambda also will give you speed of light. These basic aspects we are familiar, which is studied for any general wave, can be used here. But C is equal to 1 by square root of mu naught epsilon naught is one of the very fundamental relations of electromagnetic theory, which will be useful. It's derived from the Maxwell's theory. Very, very important. That's the first evidence of electromagnetic wave speed in terms of two universal constants. Okay. Now we just look into the electromagnetic spectrum. How do you visualize the electromagnetic spectrum? All of you studied the electromagnetic spectrum. Starting from one side, we have radio waves. Then if you reach the other end, you will end with the gamma rays. Radio waves are useful for radio communication, and gamma rays are very harmful radiations. In terms of penetrating power also, if you look at it, radio waves and microwaves, infrared rays, even light, the first four will not harm much. And ultraviolet, X-ray, gamma rays, they are highly penetrating rays. They ionize the matter, therefore they are harmful. In terms of wavelength, if you look at it, radio waves has a wavelength greater than 0.1 meter, whereas microwaves 0.1 to 1 millimeter. Infrared 1 millimeter nanometer, that is very important. Visible range of wavelength 700 to 400 nanometer. Then ultraviolet is still higher frequency or lower wavelength, that is 400 nanometer to 1 nanometer. Here 1 to the power minus 3 nanometer, that means it is even in picometer, 10 to the power minus 12. Now altogether it becomes 10 to the power minus 12 meter, that is a picometer, 10 to the power 3 and minus 9, 10 to the power minus 2. Here gamma rays are very, very harmful, 10 to the power minus 3 nanometers and greater than that, lesser than that. Hence, it will be very harmful. But remember, radio, micro, infrared, and light do not harm. All other three will harm. Now, what are the sources of these uh, radiations? You can see radio waves are produced due to the acceleration or deceleration of electrons in areals. They can be produced in various means. Whereas microwaves can be produced using a device called klystron wall, klystron oscillators are there, magnetrons are there, even a semiconductor device called gun diode also produces the microwave. Gun diode also produces microwaves, a semiconductor device. Therefore, klystrons, magnetrons, and gun diodes will produce microwaves. All the molecules and atoms vibrate and they give rise to infrared radiations. Similarly, atomic level you find that electrons in an atom emit light when they move from one energy level to another excited level. Therefore, excited levels of various atomic structures will give rise to light. Similarly, ultraviolet radiations are given by inner shell of electrons. Suppose one electron is moved from one inner shell to the other shell, then you find that these transition from one state to another state will give rise to some radiations which will be in ultraviolet range. Similarly, higher the innermost shells of electrons are bombarded with another electron, then they emit X-rays, which are generated even by X-ray tubes. X-ray tubes or inner shell electrons will also give rise to electrons, the X-rays. All the radioactive elements will give rise to radioactive decays in the of nucleus. Most of them will give rise to gamma rays, like cobalt 60. It's a gamma emitter. It's a very, very harmful emitter, which is, have medical applications. You know that it is, can be used for treatment of cancer and other diseases. Okay. How to detect them? Radios can be detected using receivers. Normal receivers are antennas or aerials, which is of different shapes. It may be dipole antenna, then the dish antenna, all types of antennas will detect the radio waves. And microwaves are detected by point contact diodes, which are sufficient for their detection. For temperature, that is, infrared radiations are detected with help of thermal sensitive devices like thermopiles, bolometers, infrared photographic films, etc. You know, the infrared cameras are there where they use infrared films there. Then light, visible lights are detected by eye, and photo cells, photographic films, all will detect visible light. Photo cells and photographic films are used to detect the ultraviolet light. Similarly, X-rays are detected by the X-ray films or called photographic films. Even Geiger tubes, ionization chambers are all used to detect the X-rays. Even gamma rays can be detected with the help of ionization chambers, the various scintillation counters, etc. Next point, where they are useful. After studying the electromagnetic waves, you must be knowing where we are using these electromagnetic waves, because today's life is mostly because of the electromagnetic wave, including this talk now, which is online, because it's possible only because of the electromagnetic waves. If you look at the radio waves, today we have radio communication, the various type of radio communication. I write it here. Okay, radio communication. Okay, so you have the point of radio communication, radio, radio, possible because of radio waves of various frequencies. Okay, we have radio waves of various wavelengths or frequencies. As a result, today we have all the radio communication. That is the application of radio waves. Then when you think of microwaves, all even microwave ovens, okay, microwave ovens works based on the principle of that, and it is useful for treatment of several diseases as well. Treatment in medical field, we can use them. Okay, that is the microwaves and ultraviolet radiations. Ultraviolet radiations are useful for cleaning purpose. That is, say, by exposing ultraviolet radiations, we can kill all the germs in medical applications. Okay, even it is useful to treat the vegetables or any other things of that kind. Okay, so that they can be removed of all the germs which will harm them, okay, spoil them or root them. Okay, therefore this kind of applications you find that in ultraviolet radiations. Visible light, you know that very important for all our day-to-day activities. Visible light is very useful. Then if you look at the X-rays, today we are familiar with X-rays. X-rays are first of all for diagnostic purpose, that is in the medical field, correct? Diagnostic medical field, very useful. Similarly, they are useful for scanning purposes. Okay? Scanners. If you go to the airport or railway station, the scanners are kept where X-rays are sent through the materials to detect what type of items are available inside that. Therefore, they are useful in scanning applications. Then gamma rays, as I told you, although they are very harmful, they are very useful for medical applications like cobalt 60, useful for treatment of cancer. Okay, treatment of cancer like disease. Okay. Similarly, the IR sensors. Today we have IR infrared radiations. IR sensors are very useful, starting from your TV remote, okay, to IR camera. All these you find their application in various fields of our life. Therefore, by knowing electromagnetic waves, you realize what type of applications do they have, and how they will be very useful for our day-to-day life. Therefore, in today's lecture, we have covered the basic aspects of Maxwell's equations, starting with the four equations, and what is the inconsistency of fourth equations of Maxwell, which is corrected by Ampere, and finally the electromagnetic wave and their applications. I hope this class will be useful for you. Thank you. Any questions if you have, you can please ask.
Thank you, sir.
Thank you.
So,
Do they have any questions or anywhere?
so ask any questions, dear students. So chat box ಅಲ್ಲಿ ಯಾವುದು questions ಇಲ್ಲ sir.
Okay, okay.
So later on ಕಳಿಸಿದ್ರೆ ನಾನು ನಿಮಗೆ I sent through mail, sir.
Yes, yes, sure, sure.
So thank you, sir. Thank you very much. So
Thank you, thank you.
it's an immense pleasure to thank you, Chandrashekar Shetty, sir, for this wonderful speech on electromagnetic waves. This talk has given many information to the student. I gratefully thank you, sir, from KSTA and personally. And I also thank our KSTA CEO, sir, Dr. Ramesh, sir, for this encouragement to organize this talent search program. I am gratefully thank you, sir. And I
Thank you.
also thanks our chairman, Professor Ayappan, sir, and colleagues, technicians, and staff members for their participation to conduct this program. Once again, I thank you, each and everyone, and I also thanks to our all attendees. Thank you, sir. Thank you very much, sir.
Thank you, thank you.